Hey everyone, welcome to day 2 of our differentiation and integration challenge. So today, for the differentiation part of things, we have y is equal to the ln of sine squared x. So we're going to use chain rule. That's it. And then we have this integral to integrate. And we could use the binomial theorem and use Pascal's triangle to get your coefficients and expand it all out. But that would be a really arduous ordeal. And so we're going to use the u substitution to make that a lot faster. We'll do that in just a moment. Let's start with the differentiation. So if y is equal to the ln of sine squared x, then our derivative function, dy dx, or y prime, whichever you'd rather. When we differentiate ln, we do 1 over whatever is inside of the ln. And so we'll do 1 over sine squared x. And now we have to multiply that by the chain rule times the derivative of what's inside the ln, so times the derivative of sine squared x. Sine squared x is the same as sine x in brackets squared, and so the chain rule applies, right? So we have the exponent of 2 multiplies out front, 2 times sine x, and then chain rule times the derivative of sine x itself, which is cos x, and so times cos x, right? And now we can simplify that all together. One of the sine x factors is going to cancel out nicely, and so all we have left when we multiply through is 2 cos x over sine x. And then cos x over sine x, you might know, is one of the reciprocal trig ratios. And so we could even simplify a tiny bit further. We could say that our derivative function, dy dx, is 2 cotan of x. And there is our derivative. Now, again, for the integrating part of things, we could use the binomial theorem and expand that all out in a 10th degree polynomial, right? Integrate term by term. Again, that would take super long. So what I suggest doing is making a u substitution. Let's let u be that expression inside of the bracket to the power 10. And so let's let u be 7x plus 3, right? That's going to make our du not all that difficult to deal with. Du dx is going to be 7. So that means that du, our new differential, is going to be the derivative of this, which is 7 times the differential dx. Now, what we want is just dx on its own, because that's the only thing we really have present inside the integral. And so to get dx all by itself, let's simply divide both sides by 7. And so then we get dx all by itself. That's what we want to replace, right, with something, including du. Du over 7 we can rewrite as 1/7 du, and now I can make this substitution in some sense, right? I can replace dx in some integral with 1/7 du, and I'll do just that. The 1/7 is a constant. I'll plot that outside the integral. So let's do 1/7 times the integral over. Now, all we have inside is 7x plus 3. That's what our u substitution was. And so all we have is u to the 10, and then times our new differential du. And now we're set to evaluate this integral with respect to u. And so that'll be 1/7 times integral of u to the 10 is raise the exponent by 1. So u to the 11, and then divide by that new exponent. So over 11. And don't forget your constant of integration, plus c. That's a good habit to build. And now we can de-substitute back into our original variable x. We can multiply the denominators, and so we'll have u to the 11, meaning 7x plus 3 to the 11, all over 7 times 11 over 77. And again, not being forgetful about our constant of integration, plus c, and we're done. So that's it for day 2. If you guys have any good questions about derivatives or about integrals that you'd like to see done in a video, or that you just thought was kind of cool, please let me know in the comments below. That would be super helpful. And I hope this was helpful. So thanks for watching, and I'll see you for day 3.